Chapter 2, Trigonometry, Lesson 2, Trigonometric Graphs and Solving Equations using Radians. So I'm going to suggest that you don't actually make any notes on the graphs themselves because we will provide a worksheet with a clear printout of the graphs. If you want to sketch them yourself, that's fine, but you will have access to the resources to do this. Now, take a look at this graph of y equals sine x. It should be very familiar to you. Look at the x-axis. It's very clear that this is running in degrees from 0 to 360 degrees. And the points on this graph, for instance, 91, sine of 90 is 1, should be very familiar to you. Now, so far, all of the graphical trigonometric work you have done has been in terms of degrees. And we're going to ask ourselves the question, does it actually make the most sense to do this? For instance, look at the x-axis. From here to here, that's a unit measurement of 30. But look at the y-axis. That's 0 to 0.5. So we've got two very different scales on our x and y axis, but of course we shrink our x-axis to allow us to be able to see the traditional shape of the sine wave. Now, here's another graph of y equals sine x, but this time on the x-axis I've stretched out the scale, which is still in degrees. Okay, you can't see the whole thing, it's not running all the way up to 360 degrees, but the x-axis is still in degrees. But this time, I've made the scale on the x-axis match the scale on the y-axis, and you can see that here and here, where each one of these large squares represents 0.5. Now, you can just about see the starting point of the sine wave shape, but it's not recognisable. It's not the same shape that you are used to seeing because it's stretched out so far along the x-axis. So when you actually put a genuine square scale on both axes, if you're working in degrees, it's very hard to see the traditional shape of the sine wave that you are used to seeing. So the question we have to ask ourselves is what happens if we now set our x-axis in radians rather than in degrees, and that is what we're going to do. So here is the graph of y equals sine x, starting at 0 here. Obviously it carries on previously before 0, but I've taken a snapshot starting at 0 and ending at 2 pi. So instead of 90 degrees, I have pi by 2 radians. Instead of 180 degrees, I have pi radians. Instead of 270 degrees, I have 3 pi by 2, and instead of 360 degrees, I have 2 pi. Now, this makes much more sense. If you actually work out what the value pi by 6 is, for instance, which is marked on the x-axis, pi by 6 is equal to 0.523 ... So it's actually a very similar value to 0.5. So we have a scale that makes much more sense, matching on the x and y axes. And you can see that the shape of the sine wave, as we expect it, stays true to its traditional form. And this is what we expect to see when we draw a sine wave. And you can see that the graph actually makes a lot more sense when we draw it in radians on the x-axis than when we draw the graph in degrees. And you can match your x and y axes much more closely. So here is the graph of y equals cos x. And it's the same shape that you would expect, except we've drawn the x-axis again in radians rather than in degrees. So the shape is exactly as you would expect, but look very carefully at the markings on the x-axis. It's really important that you understand that cos pi by 2, for instance, is equal to 0, because pi by 2 radians is the same as 90 degrees. Cos pi is equal to -1, and we know that pi is the same pi in radians is the same as 180 degrees. So here's the shape of the cosine graph in radians. And finally, here is the graph of y equals tan x. Now, of course, the tan graph has the interesting property of having some values for which it is actually undefined. So we know that tan of 90 and tan of 270 are undefined values. So there are asymptotes for the graph at these points. But of course, working in radians, rather than an asymptote at x equals 90, the asymptote is at x equals pi by 2. And again, we don't have an asymptote at 270 degrees if we're working in radians. We have an asymptote at 3 pi by 2 radians. Now, it's difficult to show on a small y-axis scale the graph creeping closer and closer and closer towards those asymptotes and becoming infinitesimally close to those asymptotes. But if we stretched our y-axis upwards, and I've limited my y-axis from -5 to 5, you would see the graph growing infinitesimally closer to the asymptotes. If you want, you could explore the shapes of these graphs further on your graphical calculator or on Desmos software. So having explored the trigonometric graphs working in radians rather than working in degrees, we're also going to have a think about the unit circle working in radians. Now, so far, when you've worked in degrees, you know that this point here represents an angle of 0 degrees. Up here, 90 degrees, marking the first quadrant, 180 degrees, marking a halfway point on the circle, 270 degrees here, 3/4 of the way around, and then of course 0 degrees, and then 360 degrees matches back up. Now, if we want to work in radians, 0 is still 0 in radians, but 90 degrees we can express as pi by 2. So a quarter turn represents pi by 2 radians. 180 degrees can be thought of as pi radians, 270 degrees as 3 pi over 2 radians, and then 360 can of course can be thought of as 2 pi radians. Now, those of you who use the unit circle for solving trigonometric equations will remember that in the first quadrant, all the trigonometric functions sine, cos and tan are positive. In the second quadrant, sine is the only positive trigonometric function. Tan is the only positive trigonometric function in the third quadrant, and cos is the only positive trigonometric function in the fourth quadrant. Some people like to call this the cast diagram, C-A-S-T, or use other mnemonics to remember the positions of the 4 letters. Now, a little bit later on, we'll be looking at using the unit circle as a method for solving trigonometric equations because it is one of the methods that we can use to solve trigonometric equations, and quite a few people prefer to solve trigonometric equations using this method. So what we're going to do now is have a look at solving a series of trigonometric equations working in radians rather than in degrees. I'm going to start very, very simply, and we're going to solve the equation sine theta equals √3 over 2, and look at the range for our answer. Any angles we give have got to be between 0 and 2 pi radians. So check that your calculator is in radians. Make sure you remember how to toggle between radians and degrees on your calculator. Remember, if you're doing this, you need to press Shift and Menu, which allows you to access the setup options. Scroll down to angle using the arrow keys, and then use F1 or F2 to toggle between degrees and radians depending on which you need to use. For the moment, we're working in radians. So first job is of course to use the inverse sine function, sine to the -1, to work out what the principal angle is. So sine to the -1 of √3 over 2. What does that give us? It gives us an answer of pi by 3 radians. So there's our first angle. Now I'm going to solve the equation and find any subsequent answers that lie between 0 and 2 pi radians in 2 ways. So method 1, I'm going to sketch the graph, and I'm going to use the periodicity of the graph to find the other answer. So this is very good practice for sketching trigonometric graphs. As you can see, I've set up some axes for myself to use, and let's sketch in. It's actually a lot harder to do this with pre-prepared axes than it is just freehand on a blank piece of paper. There we go. We have a sketch of y equals sine x. Now, root 3 over 2 is some sort of positive value. It's equal to 0.86 approximately, 866 approximately. So what I'm going to do is I'm going to draw in a horizontal line to represent root 3 over 2, which will probably be about here. So there's the line y equals root 3 over 2, and here's the graph of y equals sine x. Now, where these two graphs meet, we have solutions to the equation sine theta equals root 3 over 2. So we've got one there, and then we've got one there. Now, the first answer is, of course, our principal answer of pi by 3 radians, and we then need to use the periodicity of the graph to find the second answer. So the easiest way, I think, to do this is to use the fact that this answer here is pi by 3 radians from the origin, which means that this answer, using the symmetry, is pi by 3 radians back from the answer of pi. So this angle here, this second answer, is equal to pi subtract pi by 3. So our second possible answer for theta is equal to pi subtract pi by 3, which is equal to 2 pi by 3 radians. And always check, input sine 2 pi by 3 on your calculator to check that you have got the correct answer. So this is method 1, where we use the periodicity of the graph to solve the equation. Now we're going to have a look at an alternative method where we use the unit circle. Of course, some of you might describe that as using the cast diagram to solve the equation. So I'm going to draw myself a pair of axes like this. I could draw the circle on as well. I'm actually not going to draw the circle, as we can do this without the actual circle shape. We just need to remember that all sine, cos and tan are positive in this quadrant. Sine is the only one that's positive here. Tan is the only one that's positive in this quadrant. And cos is the only one that's positive here. We also need to remember the angles, 0, pi by 2, pi, 3 pi by 2, and of course 2 pi radians takes us back here. Now we are solving sine theta equals root 3 over 2, and we know that the principal answer to this is the value we got earlier on. It's this value of pi by 3, which is a positive angle in this quadrant here. So we know we've got our principal answer of pi by 3. Now we then need to reflect into another quadrant where sine is still positive. So the only option is to reflect across like this, and then the angle that we will be looking for is this angle over here, and you can see that we've got pi, which takes us all the way round, but we don't want to go all the way around, we want the orange angle. So the orange angle is equal to pi subtract pi by 3, which again gives us 2 pi by 3. So there we go, that's the alternative way of finding the other answer. Now in both cases, remember, there are two answers to this equation within the set value of theta values that were allowed, pi by 3 and then 2 pi by 3. So you've got two different methods of solving your trigonometric equation. So let's have a look at a second example. We're going to solve 2 cos theta equals 0.8. Now, this equation needs a little bit of work first of all. Divide both sides by 2. So we have cos theta equals 0.4. And then again, we're going to use the inverse trig function to work out our principal angle. Now, this is not going to give us a neat value for theta, a nice exact multiple of pi. It's going to give us 1.15927 ... radians. So you can use the C symbol for circular measure, or you can just write rads or radians next to your answer. Okay. Now, really important that we have knowledge of the exact value here. So what I'm going to do is I'm going to store this in a calculator memory. Okay, make sure you remember how to do that and that you practice storing values in calculator memories. So I'm going to store this in memory A. Now, I'll round my answers at the very end in case you're wondering why I haven't rounded my final answer. I'm going to now solve the equation. Again, I'll use two methods. The first method I'm going to use involves me sketching a trigonometric graph for y equals cos x. Again, like I said, a lot harder to do on pre-printed axes than when you sketch the shape of the graph roughly. So there's my graph of y equals cos theta, or y equals cos x. And what I'm going to do is draw in a horizontal line at 0.4. because I'm solving cos theta equals 0.4. So 0.4 will approximately be there. It doesn't really matter because we're not doing an accurate graph intersection here. We're just using the periodicity of the graph and the symmetry of it to help us. So there is the line, y equals 0.4, and you can see the two intersections that occur between 0 and 2 pi radians. There they are. Now, this one over here is the answer of 1.1592 ... Notice it's just coming up before pi by 2. Now, what is pi by 2 as a decimal value? It's about 1.5, so you can see this makes sense in relation to the graph. Now, there's another answer that we have to locate over here. So again, use the symmetry of the graph to do this very carefully. I can see that this distance matches this distance here. So I can simply take away that value of 1.1592 away from 2 pi to get the second answer. So my other value of theta, my second answer, theta equals 2 pi minus 1.1592, etc. And because I've stored that in a calculator memory, it's easy for me to access it if I do something else on the calculator, and that gives me a value of 5.1239 ... So to finish off, I need to give my answers rounded, so theta equals 1.16 radians, and the alternative value, theta equals 5.12 radians to 3 significant figures. Or if you want to, write rads or radians rather than using the C symbol. So again, I've solved this equation. Method 1, I've used the trigonometric graph. Now, we're going to have a look at solving again by method 2, which is to use the 4 quadrants and the cast diagram, or the unit circle diagram. Now, it's important to make sure you know the size of angles as approximate values, even if they're multiples of pi. So for instance, 2 pi we know is about 6. Pi by 2 we know is about 1.5. Pi, of course, we know is about 3. And 3 pi by 2 we know, which is over here, is about 4.7. So very, very useful to know the approximate values of angles. Remember, we've got to find answers in the range 0 to 2 pi, but you're working with decimal values of theta here, not exact multiples of pi, not fractions of pi. So here, we've got two answers, 1.16 radians and 5.12 radians. It's important to check that they are actually within the range. So you can see that we've got an upper range limit of 2 pi radians, which is about 6.28. And we can see that 5.12 is clearly within that range, so we're okay. So it's always good to know, even if you're dealing with fractions or multiples of pi, what those values are as decimals. So here we go. Let's label the quadrants. Everything's positive, sine is positive, tan is the only one positive, cos is the only one positive. So we were solving cos theta equals 0.4. So that's a principal angle, which I'm going to draw in this quadrant over here. And we know that that angle there, that's our 1.16 radians that we worked out. And I need to now reflect that into another quadrant where cos is positive, because again, I'm solving here, cos theta equals 0.4, and 0.4 is a positive value. The only quadrant I can flip into, which is where cos is positive, is down here. So the angle that I want is this angle here. Now, how do I get that angle? I either have to go all the way around like that, or I could simply use the fact that it's 2 pi and then I'm subtracting this 1.16 degrees that's over here. So again, my second angle can be calculated as theta equals 2 pi take away 1.159, etc., which gives me the 5.2 radians as my second answer. And of course, you get the first answer just by using the inverse cosine at the beginning. So you will have seen these two methods in lessons when you've solved trigonometric equations. People quite often have a preference for one or the other. Work with whichever method gets you to the correct answer efficiently and accurately. So let's have a look at example 3. We're going to solve 2 cos squared theta equals cos theta. Now, why have I included this example? I've chosen it very specially because people have a real temptation to try and divide through by cos theta. And I'm going to say, do not divide by cos theta. Factorise. The key to solving this equation is to subtract cos theta from both sides. So you have 2 cos squared theta minus cos theta equals 0 and factorise. So you get cos theta and then in brackets 2 cos theta minus 1 equals 0. If you divide by cos theta, you will lose potential solutions. So we now have a product of two expressions which multiply together to give us theta, is to give us 0. So we have two options. Either from here we can say that cos theta equals 0, or from the second part of this we can say that 2 cos theta minus 1 equals 0 and cos theta is equal to a half. Now I'm going to solve this equation using the trigonometric graphs. So here is my graph sketch. So first of all, solving cos theta equals 0, we get two obvious answers, both fractions of pi. Theta equals pi by 2 or theta equals 3 pi by 2. Now the second equation, cos theta equals a half, I want to draw in a horizontal line here at y equals a half. And then let's find those points of intersection. There's one there. We'll find that angle in a second. And there is one over here as well, which we will find. Ignore the fact that my sketch does not look perfectly symmetrical. It's difficult to achieve that by hand, so don't worry too much about that. But let's use our calculator to find the inverse cosine of a half and find a value for theta from that. That comes to pi by 3. So I know my first angle here is pi by 3. And then, of course, we'll use the symmetry of the graph, pi by 3 inwards from there. We want to go pi by 3 backwards from there. Again, don't worry if the symmetry doesn't look perfect on my graph sketch. It is difficult to do that by hand. This angle here is going to equal 2 pi subtract pi by 3, so that will give me my second answer within the range allowed of 0 to 2 pi of theta equals 2 pi take away pi by 3, which equals a value of 5 pi by 3. Now it's really crucial to make it very clear at the end of an equation what your answers are, and we have got pi by 2, 3 pi by 2, pi by 3 and 5 pi by 3 as a set of possible answers. I'm not going to solve this equation using the unit circle as well. I've solved it using the graphs. If you want to proceed and solve it using the unit circle yourself as an alternative, please do that. So, example 3. We're going to solve tan squared theta equals 1. Now, I've included this as an example because it's another question where people do make some silly mistakes. When you square root both sides of this, you get tan theta equals 1 and, as an alternative, tan theta equals negative 1. So many people forget the negative square root as well here. So let's do these separately. We're going to start with tan theta equals 1. And what does tan to the minus 1 of 1 give us in radians? It gives us pi by 4 as a possible answer. And then what I'm going to do is sketch the tan graph and then find the other answer. Now, sketching the tan graph, I'm going to be very careful as I do this because, of course, there are asymptotes for tan, the tan function at pi by 2 and 3 pi by 2. So I'm going to draw my asymptotes carefully in place, and then I'm going to position my tan function like that, and then like that, and then like that. Now, let's draw in a horizontal line at y equals 1, which is over there. And then we know that there are 2 points of intersection that we have to explore. One of them over here, we already know has an angle of pi by 4. And then the other intersection that we're looking for is over here, and we have to try and use the symmetry and periodicity of the graph to find the second answer. Now, here's the way in which I would do it. I would look at this portion here, and then imagine pi was where 0 was at, and you can see the repetition, hopefully, of the shape of the graph in that section there. So this angle here is going to be pi plus pi by 4, as you've got a direct repetition of 0 plus pi by 4 there. So the second answer is pi plus pi by 4, which gives us 5 pi by 4 radians. Now, because my answers are multiples of pi, I don't need to write radians or use the C symbol to indicate that I'm working in radians. It's very clear from the fact that the angles are written as fractions of pi. Now, what happens when I look at tan theta equals negative 1? Now, I know that if I do the inverse tan of negative 1, my calculator will give me negative pi by 4, which is unfortunately out of range because we're looking for answers between 0 and 2 pi. So I have to use this to help me find my missing angles. So I'm actually going to sketch the tan graph again underneath for clarity. So here it is, and I've included a little portion of the graph before 0, so going into the negative angles here. Now, let me draw in a horizontal line at negative 1. There it is. So there is my line y equals negative 1, and there is my blue graph y equals tan theta. Now, look at the intersections. There's an intersection here, which is negative pi by 4, as given to us by the calculator. And then the answers that we want that are within range are here, and then another one, which is over here. Now, how am I going to find those answers? I've got to use the symmetry of the graph carefully. Now, look at this gap here. We're drawing an arrow. It's pi by 4 radians back from the origin. Can you see the repetition here? I've got to go pi by 4 radians back from pi to get this angle here. And to get this angle here, I've got to go pi by 4 radians back from 2 pi. So one of my answers is going to equal pi take away pi by 4, and my other answer is going to equal 2 pi take away pi by 4. So my actual answers are theta equals 3 pi by 4 and theta equals 7 pi by 4, and these join the two orange answers that I had previously, which were theta equals pi by 4 and theta equals 5 pi by 4. So because of the original plus or minus in this question, we've got 4 possible answers here. Now, if you prefer, you might like to use method 2, the unit circle, to solve these equations. So let's take a look at the equation tan theta equals negative 1. Now the calculator, using inverse tan, gives us theta equals negative pi by 4. Now, what is a negative angle in relation to the unit circle? Now, if you define your angle in an anti-clockwise direction, That's a positive angle. But by convention, similarly, if you define or draw your angle in a clockwise direction, it's a negative angle. So if I want to represent an angle of negative pi by 4, I would start at the origin and then I would go round like this. So I can draw in my right angle triangle like that, and this angle here, drawn in a clockwise direction, is negative pi by 4. But of course, I want to find angles which are positive. But I need the tan of the angle to be -1. What I'm going to do is I'm going to flip this triangle so that it is in quadrants where tan is negative, because tan has got to equal -1, but where we're measuring the angles in an anti-clockwise direction, so that the angles are actually positive. So I want to ignore this quadrant here because everything's positive here, and I want to ignore this quadrant here because tan is positive here. Now, if I did move into that quadrant here, it would look like this, but I want to go in the quadrant over here because tan is not positive in this top left-hand quadrant. So the angle that I want will start here and it will move all the way round to there. This angle here is a value pi by 4, and this angle here is also a value pi by 4, but the angle I want is this angle here, and hopefully you can see that that angle is pi subtract pi by 4. Careful, don't subtract negative pi by 4, that would not give you the correct answer. So it's an answer of 3 pi by 4 in that quadrant here. Now, the other quadrant is where the purple triangle already exists. So all I have to do is go all the way around like that to get this angle, but in an anti-clockwise rather than a clockwise direction. So the angle would then simply be equal to 2 pi, take away pi by 4, which gives us 7 pi by 4 again. So these are the same answers that we got from the graph, but some of you may prefer to use the unit circle to calculate the answers. So we're now going to solve the equation 3 sine theta equals cos theta. I've included this as an example because it's one that causes people so many issues because they forget about a crucial point that really we need to try and remember. Now, I'm going to divide both sides by cos theta here. So I get 3 sine theta over cos theta. I'm allowed to divide by cos theta because it's not vanishing. It's not being cancelled from both sides, which would result in us losing potential solutions. It's still there in the denominator of the left-hand side. Now, on the right-hand side, another ridiculous mistake I see people making all the time is writing 0. No, cos theta divided by cos theta, you are dividing something by itself, you get 1. Okay? And now I'm going to divide both sides by 3, so I get sine theta over cos theta equals 1/3. And what people quite often forget is that sine theta over cos theta is the same as tan theta. You've got to memorise the identity that tan theta is equivalent to sine theta over cos theta. And I'm now going to solve this equation, and again I will use a sketch of the tan graph to do this. So I have sketched my graph of y equals tan theta and my graph of y equals 1/3. Here are the intersections. There's one here and there's one here. And then I'm simply going to use inverse tan on my calculator to work out my principal angle. This gives me an answer of 0.3217 ... Again, store that in a calculator memory somewhere safely. And you can see that that's this first angle here, 0.321, etc. So, looking at the symmetry of the graph, here's our first answer. It's 0.321 away from the origin. And then the second answer symmetrically looks like that. So my next value for theta is clearly going to be this angle here, which is pi, plus that value of 0.321, which is the size of the purple highlighted part on my graph. So theta is equal to pi plus 0.3217 radians. So if I, again, use the fact that I've stored this in the calculator memory, we can see we get this answer here when we add them together. So let's present our two answers, 0.322 radians, and the other answer, 3.46 radians, both given to three significant figures. Notice here I've just said rads rather than using the radian symbol. Remember, there are different ways of presenting your final answer and explaining that it is in radians, but because our answers are not exact fractions of pi, we must indicate that the answers are in radians by writing radians or using the little c notation. Final check. Remember, I told you to always think about the range. Your answers have got to be between 0 and 2 pi, and remember 2 pi is about 6.28 radians, so both our answers are absolutely fine and in range. So, example 6, let's take a careful look at this. Now, you have solved equations like this previously. I've included it because people often forget how to go about working through an equation like this. We are solving 2 cos squared theta plus 5 sine theta subtract 4 equals 0. Now, to solve this equation, you need to remember that there is an identity that connects sine theta and cos theta when they are in their squared formats. Okay, you must remember this. You cannot solve an equation like this with a mixture of cos squared and sine involved. So the identity tells me that sine squared theta plus cos squared theta is equivalent to 1, and that tells me that cos squared theta is equivalent to 1 minus sine squared theta, and that's perfect because I'm going to replace cos squared theta by the result on the right hand side over here. So what do I have? I have 2, and then in brackets I have 1 minus sine squared theta. Then I have plus 5 sine theta minus 4 equals 0. Now let's expand our brackets. So we get 2 minus 2 sine squared theta plus 5 sine theta minus 4 equals 0. And hopefully you can see what's going to happen here. This is of the form of a quadratic equation. So let me rearrange everything. So I get 2 sine squared theta minus 5 sine theta plus 2 equals 0. And we can factorise this. Now, if you're not sure, imagine you were factorising something like 2x squared minus 5x plus 2 equals 0. You would be able to do something like this. 2x minus 1, x minus 2 in brackets, and you're going to do something similar here. 2 sine theta minus 1, sine theta minus 2 equals 0. Don't just copy this down, make sure you can understand how to do it yourself. Now from here we get two options, sine theta equals a half, or, and the other option, sine theta equals 2. Now the second option we need to rule out straight away. We know the sine graph only goes up as high as 1, so there are no solutions to this second equation here, so make sure you rule that out straight away. The other equation we are going to take and solve, so in radians, so sine theta equals a half. So if we work out the inverse sine of 0.5, what do we find we get? We get an answer of pi by 6. So let's use the graph or the cast diagram to find the other answer. So there's pi by 6 already on the diagram, and I'm going to use the symmetry here to work out the second answer. It's simply pi subtract pi by 6, so I can get my second answer as 5 pi by 6. So the last example that we're going to have a look at is this equation here, tan 2 theta equals 1. Now, I've included this because this is another question where I've seen some really silly mistakes in the past with people trying to divide by 2 as a starting point. You can't do that. The equation is not 2 tan theta, it's tan 2 theta equals 1. Now, using inverse tan on the calculator will straight away give you the answer that 2 theta equals pi by 4. And it will be very easy to then divide by 2 and get theta equals pi by 8. But we're going to stop and pause there. The fact that there is 2 theta here rather than just a theta means that the graph will effectively double in frequency between 0 and 2 pi, which means there'll be twice as many solutions. So here is what we are going to do. I'm going to look at solving this using the graph of tan, and I'm going to sketch the graph. So have a look at the graph. Here is y equals tan x, let's say, and here is a graph of y equals 1. Now, where they intersect, we get angles of pi by 4 over here, and then we can work out the other angle over there, which turns out 5 pi by 4. But what's interesting is that we're not solving tan theta equals 1, we're solving tan 2 theta equals 1. So this angle here is a value of 2 theta, which is pi by 4. Now, let's use the symmetry of the graph to help us again. This gap here is the same as this gap here, so that second red arrow is pointing to something which is pi plus a gap of pi by 4 across here. So this value here is 5 pi by 4. It's equal to 2 theta, not to theta. So I have 2 theta equals pi by 4, and I have 2 theta equals 5 pi. 4 will divide through by 2 later on to find the values of theta. So where are my other answers going to come from? I'm going to need to search beyond 2 pi, because ultimately at the end I'm always dividing the values I get by 2, which means the answers I get will fall within the range of 0 to 2 pi. So I'm now going to sketch the tan graph beyond an angle of 2 pi. So here is the graph of y equals tan x in blue, with the asymptotes as well, and I've sketched it between 0 and 4 pi radians. I've also drawn a horizontal line at y equals 1, and the red crosses mark the intersections of those two graphs, so where tan equals 1. Now, I've marked on the two answers we already have, pi by 4 and 3 pi by 4, but there's another one here and another one over here. Now we can use the symmetry again of the whole system, the fact that this interval, and it doesn't look like it because it's difficult to sketch this, but this purple interval is always a gap of pi by 4 radians. So this value over here is equal to 2 pi plus pi by 4, which is 9 pi by 4, and this gap over here is 3 pi plus pi by 4, which is equal to 13 pi by 4. Now again, remember, you may have other ways of solving these sorts of equations. It's entirely up to you. Use whichever method you feel comfortable with and which gets you to your accurate answers. So I now know that the other options are 2 theta equals 9 pi by 4 and 2 theta equals 13 pi by 4. So where do I go from here? I have to then divide each of these by 2 to get my correct answers, and to allow for some space I'll do it up over here. So that gives me theta equals pi by 8, 5 pi by 8, 9 pi by 8 and 13 pi by 8. Now, one last thing that's worth mentioning here, let's look at the last angle, the biggest angle that you have worked out, 13 pi over 8. That's equal to 5.105, so that is within range. Remember, we're going up to 2 pi, which is approximately 6.28. If we were to work out another angle, this would be the next one, which goes after 4 pi, then that's going to be a value that when we divide it by 2 is going to give us an answer that's bigger than 2 pi, so we'll end up being out of range. So always check whether your answers are within the correct range. So we're going to finish off by just having a quick look at how we can use our graphical calculator effectively to help us solve equations and also to help us check our answers are correct. So I'm going to take the equation that we were solving just now, which was tan 2x is equal to 1. And on the graphical calculator, I am going to draw the graphs of y equals tan 2x and y equals 1. And let's have a look and see what happens when we do this. So we need to go into graph mode, mode 5 first of all, delete anything else that's there. Draw y equals tan 2x and y equals 1. Now, before I draw, I'm going to check my windows, and I'm going to set my x scale from 0 to 2 pi, and my y scale, because it's a tan graph, hang on, I'll just put my x scale in pi by 2, so because it's a tan graph, it's easier to see if we have a bigger y scale, so we'll do that. And we'll just check that this is in radians, so shift, set up, and scroll down and check your angle is in radians, we're fine. So now, exit and draw the graph, and here are both of the graphs, and then shift and G-solve, which is F5, and then intersect F5, and we have our answers. Now, you can use the arrow keys to toggle along. Now, what you'll notice is that they're not in terms of pi on this particular example. Sometimes they will be, not for fractions with a denominator of 8, but you can check that the values are correct, and if indeed you work out the angles that you had as fractions of pi as decimal values, you'll see that they are indeed correct. Now, why is this useful? This allows you to check whether or not your answers are correct. Now, in case anyone's slightly confused as to why this graph looks a bit different to the one I sketched previously when we worked this out by hand, here on the calculator I've drawn the graph of y equals tan 2x directly and the graph of y equals 1. So I can then directly find the intersections between the two functions. Previously, I drew the graph of y equals tan x, and then I had to extend its domain from beyond 2 pi all the way up to 4 pi. I then found the 4 intersections and then divided them by 2 to get the single values of theta. Here, because I'm drawing the function of tan 2x, I just need to find the intersections to get me the correct answers.